our collaboration between ITB and Akita University that has been started since 2008. The topic today's session is volcanology. Today we will discuss about the phreatic and similar eruption. Let me introduce the invited speaker, Professor Tsukasa Ohba. He's professor from, I heard that this morning, new faculty from Faculty of International Resources Science from Akita University. Okay, before we start, I will give some information. There will be a short question answer session at the end of the presentation. To ask the question, audience may use Q&A feature in the Zoom or write your question in YouTube comment section during the presentation. The question should be in the following format: name, institution, or affiliation, and question. And due to the time limitation, we will select 3 questions and continue to the remaining or if time is adequate. And before we start the presentation from the invited speaker, we have 2 sessions. First is I would like to welcome to Pak Insinyur Kasbani MSc, the head of Center for Volcanology and Geological Hazard Mitigation, to give the preface speech. To Pak Kasbani, please welcome.
Thank you, Mr. Chairman, Pak Idham Andri Kurniawan, for kindly introducing me to the audience. The Honorable the Dean of FITB, Bapak Irwan Mengilano, Honorable Professor Tsukasa, Ohba of Akita University, and distinguished participants. Assalamualaikum warahmatullahi wabarakatuh. Good morning, selamat pagi. Ohayo gozaimasu. Yeah. First of all, I would like to greet Professor Tsukasa Ohba from Akita University of Japan. We appreciate that you are able to attend this event as a guest lecturer. We are hoping to learn from your experiences. I also would like to thank the committee from Department of Geology ITB for inviting me to deliver an introduction to this lecture event. In my opinion, this event is very good and important. Hopefully, this event could help in increasing public interest in volcanology. Ladies and gentlemen, and our respected students, the paradise for research at volcano is here in Indonesia. Why? Because we are the owner of the most active volcanoes in the world. We have at least 127 active volcanoes, 6 of which are submarine volcanoes. Volcano is one of the geological hazards that can threaten the Indonesian people from time to time. The risk of volcanic disaster in Indonesia is still high, and this because besides volcano continue to erupt, the number of the people living around volcanoes is increasing over time. In the history of Indonesian volcanism, there are 79 volcanoes that have experienced eruption during the Holocene era. With this data, Indonesia leads the world in the number of volcanoes that have experienced eruption during the Holocene era. In the second place is the United States with 65 volcanoes, then Japan in the third place with 58 volcanoes, and so on. The long history of volcanic eruption in Indonesia has recorded many tragedies and sad stories. As many as 40 volcanoes in Indonesia have caused deadly eruption. There are more than 140,000 people in Indonesia died following volcanic activities. This number represents more than 50% of the global volcanic fatality. This shows clearly how Indonesia is the country with the highest number of casualties in the world due to a volcanic disaster. In this lecture, we will discuss about the phreatic eruption. Many people, not only in Indonesia, but in the world, think that phreatic eruption mean eruptions that are small in scale and are not dangerous. This is certainly an incorrect perception. This data show although phreatic eruption represent only 8% of the volcanic activities in the world, they cause around 20% of the number of deaths due to volcanic eruption in the world. This, of course, cannot be underestimated. Moreover, unlike magmatic eruption in general, phreatic eruption have precursors or signs that initiate brief and event under unclear eruption. So that the early warning volcano face enormous challenges when dealing with phreatic eruption. Phreatic eruption could also be followed by magmatic eruption, which add more complexities in our assessment. Therefore, studying and finding out the precursors of phreatic eruption are still our homework globally. In Indonesia, several volcanoes have the potential for phreatic eruption, including closest volcanoes to us, like Tampuan Prau and Papandayan. There are also Dieng and other volcanoes. In reality, these volcanoes are now visited by tourists. Volcanoes have become tourist attraction. It creates more difficult for volcanologists to give early warning. Evidence of the difficulty in providing early warning for this phreatic type eruption, one of them was exemplified by the phreatic eruption at Mount Ontake in Japan on September 27 in 2014, where even though the volcano was very well instrumented and monitored, it was difficult to deliver early warning. Even though the volcanologists, even though it was difficult to deliver warning, even though the volcanologists there could already seen change before the eruption. Why is this early warning typical? Because if we give a warning but the volcano does not erupt, it is possible that the community or visitors will lose confidence in the next warnings. However, if we do not give a warning but the volcano erupts, then the public or tourists can become victims. Ladies and gentlemen, and our respected students, the big challenges in the world of volcanology will always exist from time to time and continue to evolve. Therefore, I hope that in the future, volcanology in Indonesia can continue to develop where more and more young people are willing to develop their career in the field of volcanology and at the same time dedicate themselves to jointly strive for the mitigation of volcanic eruption in Indonesia, helping to save lives and livelihood of the people in Indonesia. I think it's all that I could deliver today. Let us now follow the lecture with enthusiasm, and hopefully we can get the knowledge conveyed by the speaker. Thank you very much. Terima kasih. Arigatou gozaimasu.
Thank you very much, Pak Kasbani, for give the preface for this guest lecture. Okay, next session is I would like to welcome Pak Irwan Melano, the Dean of Faculty of Earth Science and Technology ITB, to give the opening speech. Pak Irwan, please welcome.
Terima kasih, Pak Idam. Selamat pagi. Very good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Thank you, Pak Kisbani, Pak Kasbani, for your very important introductions. And also, I'm very delighted to welcome Professor guest lectures. I believe now it has been how many times? Maybe more than 6 times. The group of Pak Mirzam and Dr. Idams, they are very active. They are very good in connecting world-class researchers and lecturers with our students, with our department, and importantly with the Volcanological Survey of Indonesia, or Center for Volcanology and Geological Hazard Mitigations. As mentioned by Pak Kasbani, the main missions of volcano monitoring, or the reason why we study volcanology, is very simple: to save lives and property. And the volcano monitoring Indonesia, as already clearly explained by Pak Kasbani, conducted by Center for Volcanology and Geological Hazard Mitigation, this year it will be 100 years old. Although maybe the history of volcano observation in Indonesia much older than that. We already have a very good and long history of volcano study in Indonesia. And I also agree with Pak Kasbani that phreatic eruption is very important. And in my personal opinion, this part of research is still it's still very few topics. It is very few researchers who willing to study these topics. And I still remember the phreatic eruptions of Ontake volcano in 2014, 27 of September. The eruptions, I believe, was the worst volcanic disaster in terms of phreatic eruption in Japan. Maybe more than 50 or 58 people passed away and 5 people missing. And also in Indonesia, we have the same problem. For example, phreatic eruptions of Tangkuban Perahu volcano. The locations of this volcano, the volcano crater with the people makes the phreatic eruptions needs to be considered very seriously. And in terms of the Ontake, personally, I have close relation with this volcano. When I was a student in Japan, almost every autumn, I do leveling survey. Maybe most of the young generations, they cannot imagine the leveling survey, how hard and how difficult doing gravity and leveling survey. So I need to take a walk at least 10 kilos every day for the whole weeks during autumn. But for me, that was a very good experience. So I can study many things. So I can really see the importance of understanding the importance of volcano monitoring. And during these webinars, we have many young guns, young students. They will be, I believe they will become the next volcanologists together with, they will help us. They will help Dr. Idam, Dr. Mirzam to establish a better volcano monitoring in Indonesia. So I believe by having this webinar, having the expert on this field, having Professor Ohba and Pak Kasbani with us today, we are in the right directions. We are in the right time, in the right place to reduce the risk of volcanic eruptions in Indonesia in the future. So I wish you all a very successful webinar. Again, thank you very much for your time.
Thank you very much, Pak Irwan Melano, for the warm greeting for the audience. And without further ado, please welcome Professor Tsukasa Ohba from Akita University. Sensei, time is yours.
Hi, good morning, everyone.
Good morning.
Morning.
So thanks, Chairman, for introduction, and also thank you for important introduction, Mr. Kasibani and Mr. Irwan Melano. So I believe volcanology is very important in Indonesia because just there are a lot of active volcanoes, and I hope many young people could work on volcanology to mitigate volcanic hazards. And also, I hope we can collaborate with Indonesian young people, of course, other many countries. So I want to start the lecture. So just introduce myself again. I'm Professor Ohba. Maybe I should share my screen. Can you see the screen?
Yes.
Yes,
Yes,
we
we
can
can.
see it
Okay.
clearly.
Yes, it's clear.
Thank you. So I am Professor Ohba from Japan, and I am a volcanologist, and I belong to Faculty of International Resource Sciences, Akita University, Japan. And I heard this class is just a part of volcanology class for graduate students. So I guess many people have already learned basic idea of volcanology, and basic idea of volcanology includes typical magmatic eruptions like a Plinian eruption, Vulcanian eruption, or pyroclastic flows. But I have been studying a special type of volcanic eruption. So today I'm talking about this type of eruptions. The talk is entitled Phreatic and Similar Eruptions. These eruptions are characterized by absence of magmatic material and often called as non-juvenile eruptions. Juvenile means magmatic, new magma, and non-juvenile means free from magma. So sometimes we use non-juvenile, the word, non-juvenile eruptions. These eruptions are special because ordinary eruptions are characterized by magma fragments or pyroclasts. This is the contents of this talk. I will briefly define the term of these eruptions. Then I will introduce each type based on the eruption models. Then I will show you some examples. In the last part, I will show you petrological and geochemical studies on the volcanic products. So first, I define the terms. There are at least 3 types of so-called non-juvenile eruptions. Non-juvenile means eruption without involvement of juvenile fragments. And all these eruptions are characterized by absence of magmatic fragments or pyroclasts. If an aquifer or groundwater layer under a volcano is heated by a new magma, the water is heated and boils to explode. This is a phreatic eruption. Next one. Some volcanoes contain volcanic hydrothermal system under crater, which is long-lived. The hot fluid in hydrothermal system is circulating or convecting. The hot fluid is often superheated, and it can explode by the thermal energy within the hydrothermal system. This explosion does not need any external thermal energy or magmatic heat. This type of explosion is called hydrothermal eruptions. The last one is a kind of Vulcanian eruption. A Vulcanian eruption is characterized by collapse of lava plug, like this. Some Vulcanian eruptions accompany fluidal magma derived from lower part of vent, such as volcanic bombs or scoria crusts. But other eruptions discharge only fragments from lava plug at the top of the vent. This type is called ultravolcanium, and the synonym of this eruption is gas eruption. It is defined by Mastin 1995. So at least 3 types of non-juvenile eruptions, and sometimes phreatic eruption is used only for a specific type or specific model. So there is a collective term. A collective term for these types of eruptions is steam blast eruption. It's not widely accepted, but I think it may be better because phreatic eruption is sometimes means a special types. So, but actually phreatic eruption is preferred rather than steam blast eruption. But actually I like steam blast eruption if if exact eruption process is unknown and volcanic ash does not contain any magmatic pyroclasts. So here I will introduce the basic idea of each type of steam blast eruptions. So the first type is phreatic eruption. This is a typical one. Definition of phreatic eruption is an eruption triggered by heating of groundwater by magma. So the explosion is caused by flash boiling of groundwater by heat supplied from the new magma. The sudden volume change by the flash boiling results in the explosion. So phreatic eruption is a voluminous water. The water body can be an aquifer and a crater. So if the magma is involved with the ejecta, we apply the term phreatomagmatic eruption. So some authors assume that the water body, initial water body, must be cold if the term phreatic eruption is applied, but other researchers say that water body could make a hot hydrothermal system. So they say just a new heat budget is needed. So groundwater can be the bottom of crater lake or infiltrated groundwater from a crater lake. So recently, this is a recent model for phreatic eruptions. Sticks and Moore 2018 identified two types of phreatic eruptions based on a review on case studies over the world. Left figure is called type 1 or Phreatovulcanium eruption. It's a kind of phreatic eruption. It's caused by injection of volcanic gas into a subvolcanic aquifer, which can be a subvolcanic hydrothermal system. The other type, they say type 2 or Phreatosuluceum, which is caused by interaction between intruding magma and the lake water infiltrating into the ground beneath the crater lake. So they identified at least two types, Phreatovulcanium and Phreatosuluceum. Maybe this is the latest model for phreatic eruptions. So second type is hydrothermal eruption. The definition of hydrothermal eruption is an eruption ejecting at least some solid material. So this is different from geyser eruption. So at least some solid materials included, and whose energy derives solely from heat loss and phase changes in convecting hot water or steam-dominated hydrothermal system. This definition is proposed by Brown and Lawless, New Zealand researchers. So it assumes no heat supply from new magma body. This does not mean magma is not related. And usually, geothermal system in volcanic field is related to magma, but In a volcanic system, steady hydrothermal system is related to solidifying old magma. So difference between phreatic and hydrothermal is just a new heat budget from new magma. So hydrothermal system itself may be related to old magma, but this hydrothermal eruption is derived from just hot fluid in the hydrothermal system. And hydrothermal systems under stratovolcano is well modeled to understand the formation of porphyry kappa system. So this is not a volcanology study. It's mainly economic geological study. And this study by Hedenquist and Lawrenson, 1994, is mostly for economic geological view to establish the understanding of the porphyry kappa system. So if this hydrothermal system can be applied to active volcanoes, hydrothermal eruption may be related to this kind of hydrothermal system. And there are some adapted models for hydrothermal eruptions. This is just an example I forget the reference. It's very famous volcanology textbook, Moritz and Heiken. So assume high temperature geothermal reservoirs at 200 meters and 400 meters. The open cracks here, open cracks are connected and the cracks are filled with the fluid. And at 100-meter depth, there is an impervious silica layer here. This is just assumption. It's typical in geothermal field. When the crack is connected to the deep reservoir, the fluid pressure at 100 meter can be as same as the pressure at the deep geothermal reservoir as the crack is connected. So high excess pressure is built up at the top of the crack. When the silica layer failures, the fluid pressure drops quickly and the superheated fluid can boil quickly to explode. This diagram says just idea. Sudden drop of pressure can make a sonic transition. And if the overpressure is not enough, or the case of 200-meter reservoir, the fluid just discharges but does not explode. This assumes a silica layer or silica cap. And for geothermal researchers, this theory is widely accepted. But I think there are some other, there can be other models. For example, it's very simple one. If the crack is closed, the deep reservoir has a pressure of lithostatic, just load by the rocks above the reservoir. But if the crack becomes open and filled with fluid, this reservoir becomes a hydrostatic pressure. So change from closed crack to open crack becomes a change from lithostatic to hydrostatic pressures. Then the drop of the pressure can cross the boiling point. Then this results in a flash boiling to explode. But this change from complete closed to complete open may be unrealistic. Next one is just the propagation of crack model. If crack is connected to deep reservoir, the tip of crack can be high in pressure. So maybe this pressure, fluid pressure is excess, and it becomes higher. Fluid pressure is higher than isostatic pressure. Then the tip of crack can propagate upward, and at some point, the failure can occur quickly. So the pressure can be kept to a shallow part, and then a quick drop of pressure can occur. Then the fluid can boil quickly. So this may result in hydrothermal explosion. But I think this is the most effective model for hydrothermal eruption. But it's just a special case. Landslide can trigger hydrothermal eruption. Landslide is the easiest way to decompress the hot water within volcano. Aquifer is usually within the volcanic edifice, but landslide removes the load. Then the pressure can drop to explode. This makes a flash boiling. So if landslide is observed and at the same time the explosion is observed, this type of hydrothermal eruption occurs. So next one, ultravolcanium eruption. This is a type of volcanium eruption. Ash from this type of eruption is composed of only of lithic fragments. Other volcanic eruption ash contains fluidal magmatic ash such as scoria or bombs. So ash derived from lava plug at the top of volcanic vent. So okay, this is a geophysical model of explosive volcanic eruptions based on geophysical observation at 3 volcanoes in Japan and Indonesia: Sakurajima, Suwanosejima, and Sumeru. The model includes detailed motion of gas, gray part, surrounding rocks, orange part, and magma, reddish part. This is basically observed geophysical model, geophysical observation. Iguchi sensei is a Japanese volcano geophysicist. They studied volcanic eruptions in very detail. And this model also includes the lava plug at the top of vent, dark gray part. And this modeling also includes the failure of lava plug. This is typical of explosive volcanic eruption. So this model just says the lava plug failure to make ash or bombs. This model is a kind of ultravolcanic eruption. But as I said, common volcanic eruption includes magmatic fragments probably derived from lower part of vent, reddish part. But sometimes such magma part is not included, only the volcanic ash derived from the cap. Then the ash is just composed of lithic fragments. And sometimes this type of lithic rich or exclusively exclusive lithic volcanic ash is called sometimes used as phreatic eruptions. But maybe we shouldn't use phreatic eruption for this type of eruption, just a volcanic. So in some textbooks, ultravolcanic is a kind of volcanic eruptions. So maybe even if magmatic fragment is not included in the ash, that may be also volcanic eruption. So I showed three types of eruptions: phreatic, hydrothermal, and ultravolcanic eruption. The collective term for these eruptions is steam blast eruption. So definition of steam blast eruption is explosive eruptions by steam expansion from external water. So ash is composed mostly of lithic fragments, and we use the term non-juvenile. So collective term for phreatic, hydrothermal, and ultravolcanic eruption is steam blast eruption. Okay, next part. I will show you some examples of each eruption. But most of steam blast eruptions have not been well understood in terms of eruption dynamics or mechanism. Therefore, it is not easy to assign the type. And actually, it is not easy to determine if it is really phreatic eruption or not. The strict definition of phreatic eruption is very too strict. So if we understand the volcanic ash has no magmatic fragment, it's just a steam blast eruption. And sometimes phreatic eruption is applied for the eruption, but phreatic eruption means the heating of groundwater and the flash boiling. But this example is a really phreatic eruption because this is the example. This is a well-examined example by the Sticks and Moore. They defined the phreatic eruption mechanism. And Turrialba volcano in Costa Rica erupted during 2014 until 2017, and they examined by geochemical observation mostly, and they concluded this model. Magmatic gas is derived from magma, and the gas penetrates into hydrothermal system and then exploded. So this is really a phreatic eruption. This is my own observation. The eruption at Usu volcano, Hokkaido, Japan, this happened 2000. This is a type of phreatic eruptions. And I think this is one of the phreatosolutean type eruption by Sticks and Moore. The heat supply from magma is evident because phreatomagmatic eruption was followed by this series of steam plus eruption. First, this eruption lasted for maybe 3 or 4 months. Only phreatomagmatic eruption occurred on the first one day, and the following eruptions are all steam blast eruption. So there was a magma, and actually before the initiation of the eruption, magma intrusion was detected as a seismic event and ground deformation. So influence of magma was distinct. The craters located at the base of Usu Mountain, and the craters are very close to a caldera lake. The groundwater from the lake was infiltrated beneath the eruption craters. So this must be the phreatic eruption, and also I think Phreatic type eruption. And the right pictures are the steam blast eruption at Shirane volcano in 2018. And the eruption killed a soldier who was in training in a ski resort. I think this is just my opinion. This is also a phreatic eruption, but we have little evidence, so we need to examine more. So sometimes it's very difficult. So many of steam blast eruptions are difficult to determine whether it is phreatic or hydrothermal. I mean, the magmatic influence is new magma influence. There was a new magma influence, or just eruption from the pre-existed hydrothermal system. For example, the 2002 eruption at Papandayan was attributed to a change in hydrothermal system underground, according to Mazot et al. 2007. And this sounds like it was a hydrothermal eruption, but we cannot say if any magmatic contribution was absent or not to this eruption. And the right picture is the steam blast eruption at Ontake in 2014. And this eruption killed more than 60 people. So this is the worst casualty after World War II in Japan. And this was a big disaster by a steam blast eruption. Then many Japanese research groups studied this eruption mechanism, including myself. So there are a lot of research groups studied this eruption, and we reported many papers. So even after the eruption dynamics were studied, it is not settled which is better word, hydrothermal eruption or phreatic eruption. So it may be difficult. So distinction between phreatic and hydrothermal eruption is actually very difficult. And I guess you are familiar with this example. I think this is the photo of Tankman paraform taken October last year, after the eruption last year. The new crater is in the right middle here. So this you may read. Oh, okay. You may remember the volcano erupted July 2019, last year. This was a steam blast eruption, but it is difficult to determine if it was phreatic or hydrothermal. Coincidentally, Shareza Saidina Ankasa, who is now working for Pertamina University, Jakarta, just finished his doctoral thesis in Akita University in July 2019. He studied steam blast eruptions at Tankban Paraf volcano in the Holocene age, and his final defense was 2 weeks before the eruption at Tankban Paraf last year. This figure is his important conclusion. So, according to his doctoral thesis, there are 2 types of eruptions. One is caused by failure by silica sealing in the hydrothermal system. This failure of silica cap is caused by the gas plume from the lower vent. The other is caused by magmatic intrusion into acidic hydrothermal system beneath the crater. And the right model is a kind of phreatic eruption, and sometimes it becomes phreatomagmatic eruption. But left figure, it could be either of hydrothermal or a phreatic eruption, depending on the source of gas plume beneath the silica zone. If the gas is derived from new magma body, then it can be a phreatic eruption. But the gas is just derived from hydrothermal system. It may be hydrothermal eruption. This is also a little difficult example, but I concluded this is a hydrothermal eruption. The Akita Yakeyama in 1997. The eruption occurred in the central crater of stratovolcano, but the source of the eruption was the hydrothermal system under the crater. But I will talk about this later in detail. And the next one, hydrothermal eruptions occur in geothermal fields typically, but geothermal fields and volcanic fields overlaps each other. So if volcanic activity is already extinct and geothermal field is developed, maybe that is a hydrothermal eruption. So hydrothermal eruptions are well described in New Zealand. And there are a lot of craters left by hydrothermal eruptions. You can see them in geothermal fields. In New Zealand, geothermal fields are developed in Taupo volcanic zone here in North Island. Near Rotorua city, there is a famous tourist site called Crater of the Moon. There are a lot of craters here, a lot of craters formed by past hydrothermal eruptions. But this site, Craters of the Moon, is out of the city of Rotorua. In Rotorua city, there are hydrothermal craters in the cities, and sometimes hydrothermal explosion occurs in the city, right near the house or in the parks. So hydrothermal eruptions are famous in New Zealand, but of course, there are also a lot of similar eruptions over the world, especially along the Ring of Fire and other volcanic settings. And I believe there are a lot of hydrothermal eruptions in Indonesia. I think the eruption at DM in 2018 is a hydrothermal eruption, though maybe this Twitter comment say phreatic, but it may be hydrothermal eruptions because of muddy nature of the product, small-scale eruption, and sudden burst without precursory activity. And I told you that landslide is the most effective process that hydrothermal eruption is triggered. The location is called Smikawa. There used to be a hot spring and called Smikawa Hot Spring. This landslide occurred in 1997 near Akita Yakeyama volcano, which I told you. We can arrive here from Akita city by 2-hour drive. It was on 11th May 1997. The slope of the volcano slid down probably by permeation of melted snow. You can see snow covering, but it's a spring season, so melting snow permeated into the deep ground, and the landslide of 100 meters scale triggered an explosion. Maybe out of this photo, triggered an explosion at landslide mass. There was 2 hot springs, and the explosion occurred at one of the hot springs. This is caused by decompression by the removal of load on the hydrothermal system under the hot spring. Next is ultravolcanium, but unfortunately, I'm sorry. Ultravolcanium is a type of volcanic eruption, and I have no idea to distinguish magma-rich volcanic and ultravolcanic eruption by eye observation. So this is Sakurajima's volcanic eruption. Maybe ultravolcanic eruption may be characterized by short-term burst without following lengthy emission of ash cloud, because ash is derived only from the failure of lava plug. So maybe magmatic fragments from lower vent makes a higher plume and lengthy sustained plume. So Sakurajima is famous volcano for volcanic eruption. I don't know this explosion exactly. This is typical of explosion in Sakurajima. Part of the explosions can be ultravolcanic. So Krakatau is also typically showed volcanic eruptions, but before 2018. This video is similar to the previous one at Sakurajima, but we can see incandescent or reddish fragment landing on the flank. And maybe it's a little different type. And plume is a little higher than the Sakurajima's one. I do not know exactly, but maybe it is typical volcanic, but magma-rich type. So in the next part, I will show you some examples on petrological studies of steam blast eruptions. So the volcanic ash from these eruptions does not contain magmatic fragments, and we focus on lithic fragments. Okay, so petrological studies, but it's a little different from ordinary petrology because we study lithic fragments, so non-essential fragments. And those rocks are usually altered, especially hydrothermally altered. So we focused on hydrothermal alteration in the ash particles. So I said petrological, but it's very similar to mineralogical studies by economic geologists rather than ordinary igneous petrology. So to understand the eruption processes, volcanic ash is studied by means of petrological analysis, especially for magmatic eruptions, such as Plinian, Strombolian, and Vulcanian. So there are so many papers, but mostly magmatic eruptions. But steam blast eruptions are not well studied. This one, I'm sorry, it's very small picture. This study, petrological study, was done for the 2012 eruption at Tongariro volcano in New Zealand. This was very good study, and also it is very rare case study. And I studied petrology of steam blast eruption, and I published one paper a long time ago. This is, I think I showed this slide in the last chapter. Our petrological study started after a very small hydrothermal eruption at Akita Yakeyama volcano in 1997. And this picture, that Yakeyama means burned mountain. First, we studied geological observation on field, and we estimated the volume of eruptive products. Only 3,000 cubic meters of ash was discharged about 1 hour, we collected samples from the deposit right after the eruption. We observed occurrence and collected samples. And we made polished thin sections of the ash for microscopic and SEM observations. And the volcanic ash contained abundant altered rock fragments, hydrothermally altered fragments, and also unaltered lithic fragments, that is dacite. And the dacite fragments were correlated with the old lava dome forming, lava dome. And every altered ash grain, we determined the mineral assemblage. Mineral assemblage means alteration minerals. Some kinds of minerals are easily identified with microscope, like this. This is silica-rich, quartz-rich altered fragments. And sometimes we use X-ray or, yes, this is SEM-EDS X-ray mapping. Or sometimes we use microfocus X-ray diffraction. And recently we use Raman spectroscopy to identify the mineral species. And we determined the mineral species and classified into some types. Several types of mineral assemblages were identified. And most of them are classified so-called advanced argillic alterations. I mean, silica-rich silica or pyrophyllite, kaolinite, and some sulfate minerals. Advanced argillic alteration is typical in the volcanic ash. And we determined, roughly determined temperatures and chemical feature of the alteration. And then we estimated the type of alteration or assemblage association alteration zones. And we correlated with nearby volcanoes, nearby underground structure of nearby volcano. Fortunately, we have data of deep underground geological structure in the nearby extinct volcano, because here the geothermal plant and they made drill hole studies. So we were able to correlate this geological structure, and our conclusion is that source of the fluid was estimated to be around 1 kilometer depth, up to 1 kilometer, and the fluid was about 300 Celsius degrees, and that fluid was sulfuric acid. 1 kilometer depth, yes, 300 Celsius degrees, and acid sulfate. And same method was applied to the 2014 Ontake eruption. We collected volcanic ash 4 days after the eruption and carried out petrographic analysis using SEM-EDS and X-ray diffraction. And we determined the alteration mineral assemblage in individual ash particles and identified many types of assemblage. The mineral assemblages are more than the case of Akita Yakeyama. These assemblages can be categorized into 3 alteration types in the maybe these words are derived from porphyry kappa geology. So advanced argillic alteration and silicite alteration and potassic alteration. And we correlated the old model based on old model for porphyry kappa system and applied to the geological structure of Ontake volcano. And we estimated the depth of source is around 2 to 3 kilometers. So we used this method for 2 volcanoes. And We found that the alteration assemblage is correlated with the model of alteration zones around porphyritic copper deposit, for example, proposed by Sirito. So, but we tried to, we thought we can try to apply the same method to many other eruptions, but found that correlation with alteration zones of our system and geothermal field is only for some, is useful only for some hydrothermal eruptions. So we needed different interpretations for other types of eruptions. This is one example. We applied the petrological analysis to the 1926 steam blast eruption at Tokachidake volcano in Hokkaido. This eruption killed more than 150 people by lahar associated by the steam blast eruption. So we collected samples from the flank of the volcano, and then we used a similar method, made a polished thin section and observed with microscope and the CMEDS and XRD. But the volcanic ash is composed of unaltered, partially altered, and completely altered lithic fragments, but relatively fresh, I mean partially altered and unaltered lithic are abundant. So altered lithic fragments are minor, and even we saw some kinds of alteration. The alteration minerals are not kinds of alteration minerals are not many. Just the silica mineral, alunite, kaolinite. We have seen at least about 3 kinds of minerals are found. So this is completely different from Akita, Yakeyama, or Ontake case. And these minerals indicate strong leaching of elements from rocks. But the alteration or leaching is very strong chemical reaction, but the degree of chemical reaction is not so high because most of rocks are unaltered or only partially altered. So our interpretation is that like this. So Tokachidake volcano is a typical volcano which often shows a Vulcanian type eruption. So we thought the eruption is also kind of Vulcanian or alter Vulcanian eruption. But we found that the partial hydrothermal alteration shows the strong leaching by acid fluid. And this must be a evidence of the presence of acid fluid aquifer. So probably this acid fluid can be made by the mixing between meteoric water and volcanic gas from magma body. And this strong acid made a high degree of leaching, but the leaching is just instantaneous. So the alteration stopped quickly. So unaltered rock or partially altered rocks are abundant. So area or volume of alteration is not so high. And this fluid may be related to the explosion itself. So this is a kind of phreatic eruption, and in terms of Sticks and Moore's definition, this is a type 1 or flared Vulcanian eruption. So we have examined all the eruptions too. I showed the recent eruptions, but we have examined all the eruptions recently. So all the samples were collected from geologic layers like this. The layers are old but still late Holocene layers. I mean 100 to 1000 years ago. This is an example. As the deposit covered by younger deposit and soils, we have done trench surveys on the flank of volcanoes like this. Depth is about 1.5 meters. In these 3 months, from September to November, I have done 8 trench surveys at 3 volcanoes. 4 days ago, the survey was done. Yes, this is 4 days ago. The picture of the trench survey. Now they are digging. Behind them, you can see snow is covering forest. So in blizzard, this must be the last survey of this year because of heavy snow. Maybe this is better example. It's near Bandung. We reported the Holocene tephra stratigraphy of proximal ash deposit from the central crater of Tankman. This work is done by Charles Tsukasa through his doctoral thesis. You can find this work in eJOG, an issue of last year. So here are the column sections around the crater. Red points are the locations of the columns. Ash components were identified by microscopic analysis and my componentary analysis. So grains are counted by the species. And here's many data. This is according to stratigraphy. So this bar graph shows the relative proportion of hydrothermally altered lithic fragments or rock fragments and magmatic fragments. So red bar is magmatic fragments. Others are altered fragments. So by stratigraphy, the proportion of magmatic fragments change, and some volcanic ash contains only lithic fragments. So I showed you this. So there are 2 types of eruptions at Tankman. So maybe I've already told you. So left figure is a kind of steam blast eruption. Right one is very easy because we have evidence of magmatic influence. But the left one, we have only detected the trace of upper hydrothermal system. And we assume that gas plume pushed the silica zone, but we have no idea of the origin of that gas. So it is a limitation by the petrological study. So now we are now trying to tackle this issue, and we found geochemical method is an effective way, and we have chosen sulfur isotope. So here's his doctoral thesis. Here's delta 34 sulfur isotope value, and he measured the sulfur isotope for these volcanic ash. And his conclusion is that there is an exception, but most of volcanic ash shows the magmatic gas origin. If hydrothermal origin, the sulfur isotope shows the isotopic fractionation. For example, sulfide shows the minus value, but sulfate shows a very high positive value. But the intermediate value should be derived from magmatic gas. And according to his data, most of steam blast eruption shows magmatic gas origin. So probably based on this data, tank one paragraph, this left type should be phreatic eruption derived from magmatic gas. Okay, we applied sulfur isotopic analysis for some other volcanoes. One is Ontake 2014 eruption. Sulfide shows negative value, and sulfate shows a very high isotopic value. And Ontake's case, the sulfur isotope shows isotopic fractionation. And our own conclusion was hydrothermal eruption. This is consistent. And Tokachidake eruption, sulfide and sulfate both showed intermediate value of nearly magmatic gas. So Tokachidake's case is phreatic eruption only. Phreatic eruption. So probably sulfur isotopes analysis is very effective way the origin to determine origin if it's hydrothermal or magmatic. So it is summary. Better terminology should be established for steam blast eruptions. And there are 3 types of steam blast eruptions: phreatic, hydrothermal, and ultravolcanic eruptions. And steam blast eruptions are all over the world. And petrology work on volcanic ash can reveal the mechanism of eruption and geological structure underground. And this may be future work. Sulfur isotope can be a good tool to evaluate magmatic contributions. Okay, this is the end of talk. Thank you. Oh, many.
Okay, thank you, Professor. Very interesting presentation. Now we will enter the Q and answer session, Sensei.
Yep.
If we look on the Q&A,
Oh, there are many.
question. Yes, it's very interesting. Okay, and then we have still enough time. Maybe we can start to answer from first question, yeah. Okay, from Rudy Arif Satrio. Oh, he asked many 1, 2, 3, 3
yeah,
question. Okay. First is, why does most of magmatic eruption without phreatic eruption? Then what is the cause some of magmatic eruption are processed by phreatic eruption?
I guess sometimes phreatic eruption becomes a precursory activity of magmatic eruption. This is the case of the maybe Phreatovulcanium in terms of Sticks and Moore's model, because when the magma is still underground, deep underground, the volcanic gas can arrive before the ascent of active magma. Then the volcanic gas can activate the hydrothermal system or groundwater. Then even the magma is still deep, the phreatic eruption occur. Then the magma ascend gradually. Then the magmatic eruption start. So sometimes phreatic eruption can become the precursory activity of magmatic eruption. This is my idea.
Okay, Sensei. Okay, and then next question, Sensei. What are the most content of phreatic eruption material, and how bad the impact of the eruption for people who lives around the eruption zone? Yeah. Or maybe first for the phreatic eruption material, yeah, maybe since you already showed the what is the most content of the phreatic eruption material in your set.
So I haven't mentioned about the gas component well. I have studied a petrological study, But in the last part, I showed the sulfur isotope. But I think the sulfur species are important, especially for phreatic eruptions, sulfate. We have seen sulfate, but actually sulfur dioxide or sulfur species can be discharged by the phreatic eruptions. So maybe sulfur is very important.
Yeah. Is there any specifications between the percentage, I mean, the model occurrence of the juvenile material or non-juvenile material, Sensei, from the phreatic eruption? Or all of them is non-juvenile material?
All of the volcanic ash are composed of lithic fragments in a steam blast eruption, but the proportion of altered material and other unaltered material, or sometimes just precipitate sulfate, are variable, very variable. Sometimes all the lithic fragments are fresh.
Okay. Okay. Yeah, so it's very difficult, yes, yeah.
Yeah.
Okay, how about the impact, Sensei? The impact of the eruption?
Impact.
The impact, yes. The eruption of the people who lives around the eruption zone.
Basically, the hydrothermal eruption or phreatic eruption are small in scale. So even the abundance of the toxic gas is high, but absolute volume is very small. So if people are right near the crater, it may be very dangerous, but explosion itself is more dangerous. So I don't think the chemical impact is not so severe. Just the physical impact is more around the crater.
Yeah, if related to the landslide, Sensei, it can be more dangerous or not?
I think landslide itself is dangerous, more dangerous in scale.
Yeah. Okay, Sensei, thank you. And then next question, this is from Rudy. I hope Professor Ohba know about the Lapindo. Lapindo is a mud flow,
Yeah.
which they happen at one area in East Java of Indonesia. Could you explain what the cause of the phenomena? Maybe Sensei know about what is the correlation between phenomena of Lapindo with the phreatic eruption. Is there any correlation or not? Do you ever?
I think the mechanism of Lapindo is similar to hydrothermal eruption. Maybe steam blast eruption should be applied for the active volcanoes or geothermal fields. But it's a kind of, maybe it's derived from the sedimentary layer or oil field. So mechanism is very similar to hydrothermal eruption, but it should be different.
Different observation. Okay. Okay, Sensei. Next question. This is from Animus attendee, but thank you for the lecture. Volcanology is something new for me. I would like to ask, is there any relation between phreatic eruption and the Maar formation? As I see on the mountain Gamalama, it has two maars in distal area. Does it mean that the magma column is tilted, or is there any other sources hitting the rock?
Yes, and basically malformation is correlated with phreatomagmatic eruptions. But in my opinion, phreatomagmatic eruption and phreatic eruption are very similar. Just phreatic eruption has no involvement of magma. It's just a coincidence. Magma and water body close relation. It just sometimes magma is involved in small amount, and usually malforming phreatomagmatic eruption contains abundant magmatic fragments. But phreatic eruption can make a malformation.
Okay, Sensei. Okay, next question from Pak Andri Subandrio. This is our colleague ITB. The question is why you compare the volcanic eruption phreatic with the porphyry copper system. In the porphyry copper system, there is a dioritic intrusion deep below the crater.
Maybe other types of OVA system related to volcanic activity should be compared. But currently, we just correlated the porphyry copper system because common subduction zone stratovolcanoes are well correlated with the porphyry copper system. But there must be some others. For example, caldera volcanoes should be different type, and or submarine volcano makes a different type of eruptions, steam blast eruptions, and maybe different type of OR system zonations. It's just our conclusion. Only we tried porphyry copper system, but others should be considered.
Yeah, before next question, I would like to give the opportunity to our colleague from ITB, Pak Mirjam, or from PVMBG, Pak Devi, or give direct question to Professor Ohba. Please, Pak Mirjam or Pak Devi.
Maybe we can continue for the next question from the audience.
Oh, okay.
Yeah.
Okay.
Yeah.
Okay, Pak Mirjam.
Yeah. There are also some question on the chat room.
Okay.
Yeah.
Okay. Yeah, many actually, yes.
Yeah.
Okay, Pak Mirjam, I will continue to the Q and answer first. So from next is from the Pak Azri Ejriat Putra Muhammad. What is the main difference between fragment or as product we found in magmatic eruption, steam blast eruption, and hydrothermal eruption in petrographic transition? Second, can we assume directly about the hydrothermal eruption if we found some or a lot of alteration with some specific economic mineral?
The first question,
Yes.
difference between fragment ash product we found in magmatic eruption. It's basically the abundance of magmatic fragments. We call it pyroclast. Pyroclast includes a bubble wall type volcanic ash, scoria, pumice, and they are all fresh, fluidal, or vesicular magmatic fragments. But other steam blast eruption or hydrothermal eruption, they are all lithic fragments. Lithic fragments sometimes volcanic rocks, so sometimes it's very difficult. But it's just a fragment of lava or altered lava, or sometimes non-volcanic rocks. So maybe you can easily distinguish from magmatic and other steam blast eruptions. But steam blast eruption includes hydrothermal, phreatic. It's sometimes difficult. Okay, the second.
The second is, how about we assume directly about the hydrothermal eruption if we found some or a lot of alteration with some specific economic mineral.
Maybe we cannot jump to the conclusion that it is hydrothermal eruption because many volcano involves a hydrothermal system. So sometimes in Tankman-Paraf's example, magma can penetrate into hydrothermal system. So magma and altered minerals can be discharged at the same time. Actually, Charles and Kassa found energized energized in a volcanic ash, but it is with scoria fragments. So it must be very careful to determine.
Okay, we still have time, Sensei, and then maybe before to Q and answer, I will jump first to the chat column. There is also a question. This is from Fadila from ITB. From the three types steam last eruption, which most dangerous for society, Sensei?
Most dangerous.
Yes, most dangerous. Three types steam last eruption.
Steam blast.
Blast eruption.
どれだろう。It depends. It depends, but basically hydrothermal eruption is small in scale. But I have to say it depends because you know the eruption in DN 2018. There were a lot of tourists, and maybe that eruption was very small in scale. You know, in Indonesia, there are many active volcanoes like Sinabung or Merapi, but nobody goes to the crater of Sinabung or Merapi during the eruption. But many people can access the active crater of DN or other hydrothermal eruption volcanoes, and they erupt without any precautionary. So social impact is sometimes big, even if the eruption is small, such as hydrothermal eruptions. So I cannot say the type. But a problem is that people can access the craters or volcanoes, and sometimes all these three types cannot be predicted, and sometimes it erupts suddenly.
Okay, Sensei. Yes, we still we should learn, yeah, Sensei, yeah? More specific. Okay, next question is about from Pak Fitri from UPN, Sensei. Maybe you know him. Whether submarine volcano also a eruption? This is from the column chart. Whether the submarine volcano also a phreatic eruption?
Actually, I have no experience studying submarine phreatic eruption, but I think must be. Must be.
Okay, yeah, because of many of water, yeah.
Yeah.
Okay. Okay, Sensei. Next question from this is the Prof. Pak Andri, our colleague. He asked continue from the previous question. What is the significant difference between phreatic and hydrothermal eruption? Is both phreatic and hydrothermal same manner, which is from the both P and H was triggered by magmatic intrusion. Is there a hypersaline system, aquifer, or reservoir below the crater that phreatic eruption? Actually, there is two questions here. First is what is the significant difference between phreatic and hydrothermal eruption?
The significant difference between phreatic and the hydrothermal eruption is that the presence of new magma heat budget. Hydrothermal eruption occur only by the hydrothermal system itself. So probably it's of importance in terms of volcanic hazard. If the magma under hydrothermal system is very active or activated, phreatic eruption can be the precursory activity. But hydrothermal eruption can be triggered by, for example, seismic activity, tectonic seismicity. So usually hydrothermal eruption is not related to magmatic activity. So we should distinguish hydrothermal eruption from phreatic eruption because of the evaluation of the magmatic activity.
And maybe the second question is is there hypersaline system, aquifer or reservoir below the crater that phreatic eruption?
I have no idea about that.
Okay, yeah.
It can be.
Okay. Okay, from the column chat is almost finished, and then we jump to the question and answer. Yeah, to the Q and answer again. This is I will continue from the M. Dari Hilmi Hasibuan. This is from ITB also. How to distinguish Phreatovulcanian and Phreatosatsean eruption types throughout past eruption products?
Maybe it's a little difficult. Because it's difficult because the authors proposed this classification in a 2018 paper, and the data are based on modern eruptions, at least recent eruptions. So Phreatosatsean is related to crater lake. So it's just an observation. And maybe, yeah, actually Sticks group is trying to find out this distinction. So maybe they will publish the paper about this topic.
Okay. Yeah, we waiting about that one. And then maybe this is the last question from Aditya Saputra Sensei. Oh, before that one, from Aderisman Sensei, sorry. Aderisman from STTMI Bandung. Thank you for the lecture. Is it possible to predict the next phreatomagmatic and hydrothermal eruption? What is all the parameter? What is the parameter?
Predict.
Yes.
We have two ideas about prediction, long or middle term prediction and short term prediction. Basically, long term prediction is based on geological observation, like yeah, I showed the trench geological survey, and we can understand the frequency of eruptions from geological data. For example, once 100 years. So long-term prediction can be done by geological and sometimes document analysis. But the short-term prediction must be done by monitoring or geophysical observation. Yes, it's a little difficult, and Japanese seismologists or geophysicists are trying to understand the tendency of phreatomagmatic or hydrothermal eruptions. Especially hydrothermal eruptions are sometimes difficult, but now they, for the case of Ontake 2014 eruption, they have found their special kind of precursory seismicity. So maybe seismological investigation is needed to predict phreatic and hydrothermal eruptions. Just an ongoing study.
Next, last question, Sensei. This is from Aditya Saputra, our student. Hello, good morning, Ohba Sensei. Thank you for the presentation and knowledge. My name Adit, interested phreatic eruption. I want to ask some question. How we can distinguish hydrothermal and phreatic eruption from field observation? Is it any clue or specific information to identify this eruption? Second question, is there any influence with the type of water, freshwater or brine or crater-like water, if they are interact with the heat to eruption? And the third question, how we can mitigate the predict or eruption, because I guess this is very unpredictable eruption. Number three, maybe we already answered, I say.
Yeah.
But how about number one? Actually, yep, in the field observation. Sensei distinguish.
Yeah, it's an essential question, but it's very difficult to answer. I can say we are just trying to the clue to this distinction between hydrothermal and phreatic. If the eruption occurs in a geothermal field on the extinct volcano, it can be hydrothermal eruption. But on the active volcanoes, it's very difficult. So there may be some clues, but I have no idea about that. We need to study more.
Okay, Sensei. Maybe this is the last question and the last also of the this lecture, Sensei. So, ladies and gentlemen, we have finished the guest lecture of today. We have learned a lot today regarding phreatic and similar eruption. May what we have learned today will be useful for us in the future. Before we close this session, let me inform you that next week we will have another interesting guest lecture. Please check the date throughout official Instagram of Faculty of Earth Science and Technology ITB. Before we close, we will have photo session. Please open the camera for all panelists. Panelists or only
Pak Devi.
Pak Devi, ada Pak? Oh, ada Pak Devi.
Yeah.
Okay. Sensei, could you close the share screen presentation so I can take a picture? Stop first. Okay. Okay. I will take the photo. 1, 2, 3. Okay. Once more. 8 minutes. One, two, three. Okay. Thank you very much. Before I close this session, maybe Sensei will give some short closing. Please, Sensei.
Okay. So, actually, I wanted to have a lecture in Bandung today. Yeah, for this 1 year, I haven't been any travel to abroad. I plan to go to Sulawesi Island in July and maybe Bandung in October. But now I'm very happy to meet you just online. So probably next year, I hope we can see in Bandung again.
Yeah.
Okay, thank you very much. Once again, thank you very much, Sensei. I will close this case lecture.
Thank you.
Thank you to Pak Mirjam, Pak Devi, Pak Kasbani sudah ini ya, Pak Irwan. Thank you everyone. See you next week. Stay healthy and have a nice weekend. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam. Terima kasih Sensei, terima kasih Pak Devi.
Sensei, arigato.
Arigato.
Pak Devi ditunggu sharingnya Pak Devi ini. Yeah. Thank you Sensei. See you next time.
Yes, see you next time.
Oke. Pak Devi, terima kasih sekali sudah hadir Pak Devi. Nanti ditunggu sharingnya nih sama mahasiswa kami di sini tentang monitoring, terutama Eastern Indonesia. Kayaknya menarik nanti.
Terima kasih. Thank you, Professor Ohba. It was a very nice presentation.
Thank you.
Oke, thank you all. Pak Idam ya, terima kasih ya.
Sama-sama ya. Thank you, Sensei.
Yeah.
We will close this.
Yeah, we will close the Zoom meeting. Thank you.
Thank you.